Next presentation will be done by André Wilmes. So he is CEO and co-founder of Rafinex. So up to now, we see digitalization in manufacturing. So now this presentation will be about digitalization in design, so optimizing the design process and the design results. So André have a wide experience in optimization algorithms and makes the life easier to the engineers. Okay, so the presentation will be optimizing truly robust designs for safer, lightweight products and production rate across automotive and aerospace. So please, André.
All right, thank you, Mr. Chairman, for the kind introduction. So as was said, I represent Rafinex here today. Rafinex is an optimization company, and I would like to discuss the role or introduce the role of robust design for lightweight construction at rate. So I'm very happy that the previous speaker introduced a lot of the ideas and terminologies around what it means to produce composite materials at rate. So I would want to focus the attention to the role of design and what good or bad design is if you think about lightweight and rate production. So today I would want to convince you or show you in different ways how if a design is truly robust, so if it's resilient, if it is lenient, if it can handle not just perfect operations but also suboptimal operations, how a robustly optimized part can help move new products to market faster. And how they can help also meet all these new vehicle type and platform types that the previous gentleman from Airborne already introduced. So last mile deliveries, personal vehicles, VTOLs, all these new performing platforms that are to be produced in higher numbers than currently common particularly in the composites and aerospace sectors. And then again, as well, for the business, it's also about developing these products faster while reducing business decision risk. And it's also increasingly, obviously important, particularly also for the composites industry, with all the legislation that's already in place and probably future legislation to come, how to make sure that products are as efficient as possible and also as sustainable as possible. And so today I would want to put forward the hypothesis or the idea that if you optimize parts to be robust, then you can address in different aspects all of the above points. A quick note, as a lot of the stuff that I will be showing today and discussing today is not being developed in isolation. A lot of this is also driven through a consortium of which also the previous company is part of, at least a UK branch is part of a consortium in the UK that is currently ongoing. It is called Ascend. It focuses on tightly integrating the UK composites capabilities and the supply chain from OEMs under the leadership of GKN, and then there's also McLaren with their expertise involved all the way through the supply chain of machine manufacturers and material supplier and design capabilities. So it's really all about integrating the UK's capabilities on being able to deliver on these high performance composites parts that are to be produced at higher rates than ever before for these markets, such as eVTOLs, luxury cars, new aircraft frames, which again are to be produced in higher numbers than ever before. Rafinex's role in this part is unsurprisingly on the design optimization. So how do you go about designing components and composites parts for production at rate and making sure that they remain robust, because everybody can optimize parts, but the trick is, how do you optimize parts safely? So how do you reduce weight? How do you optimize components without compromising the safety and the risk? So just a quick word on Rafinex. I understand we are, I would say now, a young player in the market, but we're not that known yet. So we are really a company that focuses on algorithmic developments. So we are really a software company. We produce optimization algorithms and optimization software, but our focus really lies on getting the best of what is technologically, from a mathematical point of view, out there into the hands of the industry, so that they can develop their products. Formally, we are a spin-out from a mathematics institute on stochastics in Berlin, and we've grown in the last couple of years. So we have people pretty much all across Europe now, ranging from Berlin and Munich in Germany to Luxembourg to Brighton, Bristol, London in the UK. So again, our core expertise is algorithms, and even within algorithms and optimization, our kind of peak knowledge is in around uncertainty. So we are able to not just optimize components under ideal conditions, but we are able to include real-life uncertainty from manufacturing, from material properties, from load conditions. So it's all about making an optimization which creates a part which is fit for reality. So I don't want to assume anything, so I will quickly go through the basics of design optimization and how this new variant of stochastic topology optimization gets you safer design. Before that, though, I'm going to explicitly state what today is not about. We are not talking about bionic designs. We are not talking about generative design, and we are not talking about anything involving AI. Our thinking towards these things is that we wonder, as Rafinex, we wonder why these components, while they do seem to make it into concept phases, they never go beyond. So they never make it, or at least we are not aware of that many parts that go beyond the concept stage into actual series production. So, and also AI still being in the engineering sector in its young age, maybe there will be coming something of it, but that's not our business. We at Rafinex have a different opinion, a different conviction. For us, it's about using explicit the physics that we already know, finite element physics, structural mechanics, all this stuff that has been around for decades and decades, but optimizing components, so doing structural optimization of components, not classically, but doing them in a context that the part sees. So a part in operations will see fluctuations in loads. It will see fluctuations in material properties. So it's all about capturing the fluctuations of real life and anticipating this during optimization, and therefore making a part, optimizing parts that are later on, when they go and see these fluctuations, remain safe. So they are what we like to call fit for purpose or fit for reality. But none of this involves any kind of bionic design or AI or anything like that. This is straight up just explicit mathematics, very advanced algorithms, but there is no particular magic about it. So just to set the baseline on terminology, I would say. So on terminology, what does topology, classical topology involves? We usually have a design space here in gray, the gray outer box. It is an area where a component can exist, so where we give space to the computer and say, listen, the part can exist in this area. We may want, like the blue and the red rings, we may want to say, listen, here we would want to have material anyways, because we need to connect the part to something else. But then we apply some loads. So here are the loads that this part has to resist, to do its job. And then we give you a budget of, let's say, please use 300 grams. And please find me the most optimal part to do exactly this job. So that is, and then you go away and using finite elements or other techniques, you go and you do structural mechanics simulations and optimizations to then effectively create the part that is the one best part that to do the job. On top of this, I also want to use today's opportunity to dispel a myth that is increasingly, I would say, common conviction out there. When people hear topology optimization, they immediately think additive manufacturing. Well, that's not the case. You can do topology optimization for casting, you can do topology optimization for stamping. So topology optimization is not synonymous with additive manufacturing. So you can teach and you can restrict algorithms to give you solutions that are compatible with your manufacturing process. And this is key, particularly today. I mean, also the previous speaker, it's all about rate. It's all about rate, right? We can't go away and mass produce at 20,000 or 100,000 parts on additive manufacturing. Like that is not cost efficient. So just to put that out there, topology optimization does not immediately imply you have to do additive manufacturing. So what is new or different with Rafinex, so this new technology, and how does it differ? When it comes to topology optimization, you always have to say, these are the loads that my part will have to support. Here, exemplified by what we call a deterministic load factor, meaning the loads you define, they are exactly that, or you assume that in reality, they are exactly of that magnitude and exactly in that direction. But the truth is that in reality, you have variability, meaning that in operation, either the part that you have manufacturing tolerances, you have mounting tolerances, maybe in something gets mounted a little bit, just a little bit off, or worst case, the end consumer doesn't use your product just kind of exactly the way that you intended it to be used, meaning that the loads or the requirements that the part sees in operation can fluctuate. Have a little bit around what, even if you know your conditions very well, they will still fluctuate around what you assumed, right? And this is where stochastic topology optimization comes in. Stochastic topology optimization is aware or respects that from the start. So you can define, listen, this is the primary, the normal loads that we expect to see, but we are fully aware that we may have deviations from a few degrees to the left, a few degrees to the right. So this is what's exemplified here in the middle by this cone. And you can prescribe just how much deviation you want to consider and how likely these deviations are. So this is now, let's say, an augmented input to a topology optimization. But for the rest, everything stays the same. What's the why did this technology, so stochastics is also used in the financial markets a lot to evaluate risk. And this is now being used in a context of engineering is, okay, what are suboptimal conditions and what's the risk attached to that. So it's a technology that's very established in risk, stock market, and so on and so forth. But already there, the computational efforts are huge to do this analysis and let alone this optimization. And then the research that was done in the Berlin Institute enabled us to bring computational times of stochastic topology optimization down from like 3-4 weeks now to like any 20 minutes for small parts. We can do whole car chassis in about 12 hours. So it really brought the technology to an industrial use case. But what's the direct impact if I consider, if I do not or do consider variability of real life? So if we assume on the left, we have a standard classical topology optimization. So we have an area where we tell the computer, okay, we have one, this is a toy problem, but I think it exemplifies the concept quite nicely. So on the left, if we have one load, the perfect optimal shape to resist that one load in that direction is a pylon, a rod, right? And this rod will do a perfect job for that perfect assumed load. But what happens if it slightly fluctuates? Then this perfect solution will become very unperfect very quickly. Versus on the right, if you consider before the optimization that maybe there will be side loads, then immediately the stochastic optimization will find you a different shape. which we call formally robust. So it looks like a tripod, it looks like the Eiffel Tower. So it makes sense. So this exemplifies the difference between a classical optimum and a robust optimum. We can also think about it slightly differently. So if you think about optimization, generally sometimes the analogy that is being used is mountains, and it's like, how do I get to the mountaintop? A conventional optimizer will try to find you the highest mountaintop. It may get there, it may not, I can't guarantee, but at least it will try to always go to the highest point it can get, even if it's a really sharp mountaintop. So this is let's say, an optimal peak, and this is a conventional optima. Versus what the robust optimization does, it is not necessarily looking for a peak, but it's looking for a flat plateau. It's looking for the highest stable plateau it can find in the mountain range. The implication is that if something later on goes a little bit wrong in life or manufacturing, then you stay on this plateau and you don't suddenly fall off the mountain because you just stepped off the peak and you're just falling straight down. So that is the underlying technology and concepts. How does this, what are the technical advantages in industry and the impact that this can have on businesses? Oh, first I want to say that we've tested this, or we've deployed this technology for 2-3 years now in industry with automotive OEMs, but now we made this accessible through a self-service interface as well, and this launched recently. So this is a completely browser-based optimization. So this is very light touch. You can even run it on over your phone if you wanted to. So I invite every interested person to. We are currently letting people access this for trials. So feel free to reach out. So going back to robust designs, and this goes also back to us not being bionic. So what is this stochastic optimization creating?
3 minutes left, André.
3 minutes. Oh, okay.
Yes. Yes.
All right. Okay, then I'm going to have to hurry. So generally, these components are robust, so they make sense. So if engineers look at them, they recognize a lot of common sense features. So we see shells, we see U and P channels, and this leads to the components always being generally being stiffer and having better eigenfrequencies. So generally, the engineering quality that comes out of this optimizer is quite credible, and that makes sense. We can prove this, so we can also analyze this, and we can quantify this. So we can also show that these robust designs have better stress distribution and that they are quantitatively safer. So we can quantify how much safer they are, and then you can choose whether you keep this safety because you like it, or whether you're going to trade it in and start reducing weight because the safety level of your previous design was fine. How do we do this? Among other things, something that we are very proud about it is that we are using, for the specialist, the numerical people in the room, we are using adaptive meshing, meaning that our algorithm automatically optimizes the mesh resolution, the representation of the object during optimization, and this is how we achieve better speeds, this is underlying of, this also contributes to why the parts have a better engineering quality, because we can get these better shapes optimized. The business impact there is really that you can create higher performance products. They have a better safety behavior. And because they're more robust, sometimes you can use different materials, cheaper or more sustainable materials, so that there you can maybe optimize your part, keep the performance the same, but then replace it with a better different material. And as I said, these parts also, because you can optimize with uncertain requirements, so you can start the optimization much earlier in your design processes, maybe when not all requirements are known yet, but you can start optimizing and you can start making project management decisions. And typically these components or these parts won't radically change along their way. Okay, so I have 1 minute left for how partners use this. So I'm going to go back to the UK Ascend consortium and how partners in that area are using it. Oh, sorry, and what we are developing with them. So just to say, because it's composites, and I mentioned RAID earlier, these are the partners with whom we are upgrading the current status quo optimizer that is in the market. We are working on anisotropic upgrades, multi-materials, so we can optimize multiple materials and multiple components together. And then, of course, the whole thing about teaching the optimizer what is good or bad for manufacturing. So we're working on constraints for RTM, for specific AM, for inspection. So please give me parts that are compatible later on with my inspection machinery, or so on and so forth. So this is just the technology development on our end. There is a company within that consortium called FAR UK. They are a composite design and manufacturing company in the UK. So they've been using our stuff now to start doing crash, to develop early concept stages that they then turned into front crash structures, which they then also tested dynamically, and it's being built now as well. So if FAR UK, I can only recommend for their whole package in-house knowledge, from going from design over simulation and analysis all the way to manufacturing for composite parts, composite platforms. And then finally, what we are working on with GKN in this thing as well is about a blended wingtip, which is a very high aspect ratio for us component. This is a to be RTM component destined for the markets of mid-sized aircraft or VTOL, eVTOL, so really large production. So here we are working with them on optimization techniques which create robust parts, which are composites and manufacturable at these higher rates. And that's it. And I apologize for being 2 minutes over time.
Okay, so many thanks, André. So I think that we have not time for questions, but in any case, all we have the contact address to put the questions. And,
sorry,
yeah?
we do have time for that actually. So
Yeah. So we have time for questions?
Yes, according to the time schedule, he still have some time. So if you have any more words to speak, please go ahead. Otherwise, we will have some Q&A session.
Oh no, no, it was everything. I just find it a little bit quick on the last part. No, I'm happy. I prefer questions actually. So.
Okay. Yeah. So is there any question from the audience, from the floor? Actually, no. And Chairman, do you have any question or comment for him?
So not from my side. So.
Okay.
Well, then it was a pleasure.
Okay.
And then good.
Okay, so thank you very much, André, for your presentation. Very interesting, and I think that we will improve a little bit optimization that we used to make in another way. Okay. Okay. Thank you. And the next presentation.